take a look at this line. This line is this one here that's red. This is called y equals x as described below. It's called y equals x. That is to say, the value on the x-axis is equal to the value on the y-axis. So when you have a 10 on the x, you have a 10 on the y, and therefore the value that you get here will be coordinate 10, 10. This is coordinate 9, 9, coordinate 8, 8, and so on and so forth. Now, that was not to scale, of course. Of course, this would be exactly halfway, so this would be 5, 5. But the point that we need to be aware of is that there is a way to recognize and describe these straight lines. And the equation that is used is y equals mx plus c. Y equals mx plus c. M being the gradient and c being the intercept. So what we can do is we can take y equals x as just an example of a straight line and see how we can apply it to this equation to illustrate the fact that straight line graphs come in this form, y equals mx plus c. So for example, we can say that the gradient, if we're going to compare y equals x, we're going to say, well, there is no plus c, so perhaps we can assume that it's y equals x plus 0, as described here. And then from there, we can do some comparison. The intercept is c, the gradient is 1. And that means that the intercept is 0. This intercept is 0, it's a c, and the gradient m is 1. And we can therefore say that the intercept where it goes through must be 0, 0, 0, as you can see there. There is our intercept, 0, 0. And the gradient is an m value of 1, which means that as the change in y, the amount that y changes is equal to the amount of that x changes. So when y changes by 1, x changes by 1. And let's illustrate that quite quickly. We can say, you can see here that when y changes by an amount, like so, then the x changes by the equivalent amount. And so because the gradient is the amount of y that changes divided by the amount of x that changes, well, if whatever this is, let's say this is 2 divided by 2, it would give you 1. This here would be 10. The amount of y that's changing is 10. The amount of x that's changing is 10. 10 divided by 10 is also 1. So the gradient here is 1. And so y equals mx plus c allows us to have that discussion about such things as why y equals x looks as it does here. Now let's take this further. The next thing that we can analyze is this one, y equals 2x, which is this blue line here, y equals 2x. Now with y equals 2x, you can see that if we're going to compare it to y equals mx plus c, this time we get something slightly different. What we end up with is the c is still missing, so the intercept is 0, which you can see right here. It's going exactly through 0. It is intercepting the y-axis at 0. Let's make that clear again. This is the intercept of the y-axis, and it is 0. The gradient, however, this time is 2. So the change in y relative to the change in x is 2. So let's make this clear. The change in y here you can see is 4. The change in x, however, is only 2. So I'm looking at the blue line. So 4 divided by 2 is 2. And I can do this again. I can see that the change in y here is 6. The change in x at this point is 3. 6 divided by 3 is 2. So the gradient is 2 when the intercept is 0. And as a result, we have y equals 2x plus 0, wherein we do not take into account this plus 0. It's unnecessary. So we just stick with y equals 2x. Next thing that we need to consider is, what about circumstances where there is a c? Let's look at y equals 2x plus c. So we can do the same method. The method here is to compare the c. This time it should intercept the y-axis at 4, and it should have a gradient of 2. So the change in y relative to the change in x should be twice the change in y for every change in x. Let's take a look and see if we can apply that. Well, you can see here this green line, where this equation represents this green line, y equals 2x plus 4. This green line is going through the y-axis at 4, so the y-intercept is 4. And the gradient, if I take any circumstance to describe the gradient, you can see that this here is a value of 8, take away 4, which is 4, and then you have 2 as my x, so the change in y is 4, the change in x is 2, so 4 divided by 2 is 2, and thus the gradient is 2. And I can do that at any point And I can do this at any size as well. So for example, I could make this triangle even bigger and just keep the points, the concept the same. This is a change in y of 8 to 0. So it's 8. This is a change in y of 8. In fact, let me get rid of this smaller triangle in here to bring home this point. So this is a change in y of 8. You can see from 8 to 0. And if I want to go to the equivalent change in x, it will be 2 to 0 and then to minus 2. So minus 2, 0 to 2, this is 4. So this is 8 divided by 4, change in y relative to change in x, which is still 2. So it doesn't matter how big or small you make your triangle for this straight line, the gradient still can be calculated by drawing a large triangle and working out the change in y divided by change in x, which was 2. And so that is y equals 2x plus 4. Next, let's also analyze y equals 2x, but instead let's look at it in terms of numbers rather than me drawing gradients on here. So I've got this y equals 2x this time as a blue line. And what I'm going to do is I'm going to analyze certain points by looking at the numbers. Let's take the equation y equals 2x. So I take the equation y equals 2x. When x is 1, then I'm going to plug a 1 into the equation. So I'm going to put a 1 in here. That will be 2 times 1. 2 times 1 is 2. So the y value is 2. The y value is 2. So say that again. When x is 1, because the equation is y equals 2x, it will be 2 times 1. 2 times 1 is 2. So y turns out to be 2. I've written it as then when x equals 1, y equals 2 times 1, which is 2 equals 2 times 1. So the y value is 2. And of course, you can see this manifest when x is 1. There it is. The y value is 2. There it is. Now, that can be written as coordinates. I have written this as x1, y2, and we just do bracket 1 comma 2, of course. And if x is 2, it would instead be 2 times 2. So you'd have y equals 2 times 2. 2 times 2 is 4. So the coordinates you'd have would be 2 comma 4. And we can see that manifest itself here. 2 upward to this point being 4 and across there. 2 goes to 4. There's my 2 goes to 4. When x equals 3, well, of course, it will be 2 times 3, which is 6. So we'd have 3 comma 6. 3 goes to 6, which would be slightly outside. And I'm driving home the point here. As you increase your value of x, your y value goes up. And how much does it go up? Well, 2, 4, 6, 8. For every step of 1 on the x. So I went from 1, 2, 3, 4. So I'm going in steps of 1. I'm going in steps of 1 in terms of the x. But then every time I go up as a step of 1 for this equation, the y values go up as a step of 2. And this is another way of considering the gradient. The gradient, therefore, instead of considering it as calculating the change in y versus the change in x, you could also look at it as every time I increase my x value, what happens to my y value? And I've stated this phrase here, so we can see that the change in x is 1 and the change in y is 2. So it's twice the change in y for every change in x. And that's another way to view the concept of the gradient being 2. If the gradient was 3, we would see that this would go up in 1s, whereas the y values would go up in 3s. Now, let's look at it in terms of a fraction. Now, let's consider this concept of y equals 2x. We know that the gradient is 2. I'm using m for this, but we're going to analyze it slightly differently. Let's look at it perfectly in terms of its fraction. We're going to say change in y divided by change in x. And what was that change in y? Well, the change in y was 2 for every change in x of 1. But equally, what's advantageous about considering it like this is you can calculate a gradient of 2 by using other values. So you could have instead looked at when the change in y is 4, what is the change in x? Well, it was 2. And we were able to see that when the change in y was 4, right? So let's calculate this one out. When the change in y is 4, as depicted here, the change in x is 2. So we need to consider it as a fraction. This could be 150 or 2,000 and 1,000. It does not per se need to just be 2 and 1. And this is why this way of looking at it might be advantageous. You can see here, I'm looking at y equals x again. We know the gradient is 1. And so when I'm analyzing the equation, of course, you can say the change in gradient is 1 when the change in y is 1 when the change in x is 1, and 1 divided by 1 is 1. As I can illustrate this on this diagram here by saying this change in y is 1, the change in x is 1, and 1 divided by 1 is 1. But I can also analyze it as 10 over 10, or 100 divided by 100, or e over e, or pi over pi. This concept of 10 divided by 10 is absolutely the same. It produces the 1, and I can illustrate in this diagram. Note that when I have a change of y of 10, the change in x is also 10. So I'm just driving home this concept of what the gradient is and what it represents. Now this is stated as the change in y over change in x is delta y over delta x, and that's one way to write it. This implies that there is an implication here perhaps that you are able to measure the change of y and measure the change of x if, for example, we're looking at the natural sciences. Now let's do that concept, but we're going to look at it in terms of visualizing it in a more in a way that might be advantageous. So for example, relative for change in y over change in x, we can consider the change in y as a straight line across the y or parallel to the y-axis, as we've been doing. And for change in x, you can consider a straight line parallel to the x-axis. If we were to connect these up as if they were vectors, I'm going to put my change in x up over here or underneath here, and my change in y like something like that. And so what we can see is that you can then connect these up with what is often called the tangent, like so, and you have a right angle triangle. And this triangle is a way of being able to visualize the gradient. It's a mechanism to do that for ourselves. So for example, I've got 3 different triangles here. Let's say, for example, this length here we're going to call 10. So we'll call this length here 10. We're going to call this length instead, therefore, let's give it a 5. And this one, why not give it a 1? Of course, the change in x for all of these are not to scale, but assumed to be similar. 10, 10, and 10. So now we can work out the gradients, and you can perhaps see the advantage of considering it like this. So the gradient for this, of course, will be m. Change in y is 1. Change in x is 10, so it'll be 1/10. The gradient for this triangle in here, however, will be 5 divided by 10, so it would be 0.5 or a half. And the gradient for this would be the one that we were discussing earlier, 10 divided by 10, which is 1. So you can see that the steepness decreases, and the gradient discusses that. The gradient is a reflection of that steepness. It depicts it. And so, for example, if I had a straight line like this, it would be, of course, y equals x. If it was parallel to this gradient, if I had a straight line that was like this, or parallel to that line, you can see that this is a less steep than the straight line I produced that was parallel to y equals x, or the gradient of 1. And the gradient of 1/10 was a lot less steep, of course, if I try and do it parallel. And so the gradient is another phrase we could use, is that the gradient depicts the steepness of our straight lines. But this is for straight lines. Let us now move on to curves. If you have a curve, the most simple curve we're going to utilize is y equals x squared. We're going to use function notation, so fx equals x squared. These are very similar for calculus, fx and y. This literally represents x being the values we can input and fx being the values that come out, or the values that are part of the range. And we can discuss that in more detail if functions is not known at this point. But for now, there does need to be some basic function knowledge, and I judge you may have that. We can just simplify it down, however, to y is instead being stated as fx, the output value of y. So let's look at this diagram, for example. Let's do this one. If I have an input value of 1, the output value is 1. So the x is 1, fx would be 1. Or when x is 1, y would be 1. If I have an input value for the 2x, let's clean this up a bit. One more time, just a little bit, something like that. If I have an input value of 2, my output value would be, for y equals 2x, would be 4. So this equation, y equals, 2x can be seen to be represented as an input value of x multiplied by 2 give you an output value of y. That's one way to view the equation. Of course, there's the independent dependent variable way for the application of the sciences, but that's just one way to view it, and that helps with regards to the concept of stating it as fx equals 2x, where x is described as the input value here. You input values into your x, it's multiplied by 2, and the output values fx, the output values fx are come out along this y-axis here. So hopefully hopefully your function understanding is high enough for us to move on to this next point. Generally, instead of y, we're going to use fx equals x squared, and the diagram we get, of course, is our lovely quadratic. This is the quadratic we have here, and so this quadratic is y equals x squared. One thing to recognize is if I was to try and calculate the gradient, I'm going to pick the gradient at 1. This is just for ease, perhaps. So the gradient of 1, I know that when I put x1 as my input value of x, the output value will also be 1, because 1 squared for y equals x squared, 1 squared is 1. So that makes sense there. The gradient at this point, the best I can do is try and match it as much as possible at that point. And you can see that my line matches quite well. However, if I'm going to calculate the change in y and the change in x, you can see that there might be it's going to be relatively accurate, but there's a little bit of error as my triangle is so large, in that the curve is starting to pull away from the triangle, right? And so by the time I move to, say, 1.5, or by the time I move to 0.5, it's a very different curve, and I need a different triangle for that. So with curves, the gradient is not constant. For example, you can see that if I wanted to find the gradient at 0.5, I could produce this triangle, work out the change in y. So the change in y would perhaps be this line here. And I can produce another value, change in x, and I can do red divided by green, or change in y divided by change in x, and I can find this gradient. But notice it is less steep than this gradient. So the gradient changes, and what we're gonna try and do, what calculus will allow us to do, is to work out the gradient at any point along this curve. So let's analyze this. The change in x here, if I take this change in x, which we know is this line here, then I can measure it by dropping my lines down to the x-axis, reading this number, dropping my line down to this x-axis, part of the x-axis, and reading this number, and this will give me my change in x. If I want change in y, however, I will want to instead take the tip of my triangle. Remember, I can change the size of the triangle. I can make it as large and as small as I want, particularly for the types of questions wherein you have to actually use a pen and pencil. But let's just take this triangle here, the change in y. I'm going to pick the top of my triangle and say, move it all the way along to the y-axis and read that value. And this value here, move all the way across the y-axis and read that value, and I want to take them away. 1.5 take away 0.5 will give me this length in here, 1, whereas I will also be able to calculate this in here. So let's analyze that. Let's use some values. Well, this is a value of x. What it will be a number x that I can read off if this was a little bit more accurate. This length I'm going to call h. The distance from here to here, if I was to measure it with a ruler. So if I said to you, what is the length of that line? I'm going to call that length h. And x plus h will be the value that's outputted here. So if this was 10, if it were 10, and h was 5, it would be 10 plus 5, so this would be 15. If this was 7 and h was 3, it would be 7 plus 3, so this would be 10, for example. Now, this is me labeling these values here. Let's finish off by labeling the values on the y-axis. Well, the output value y we call fx. I think that was described particularly in here. I said instead of y we can use fx. The output value y we can use fx. So if we're going to do something like that, well, then what's the output value at x plus h? Well, the output value of x plus h would be fx plus h. It will be that value here of 1.5 will be the output value when, for example, this value x plus h enters in, but could be described as the input value. Again, that's not the best discourse, but could be described as the input value to our curve. So let's say, for example, it was 7, then because this is x squared, it would be 7 squared, so this value that would come out would be 49. Now, therefore, we call this fx plus h, the output value once it has gone from this value up to the line and across. And again, I'm aware there's some error with regards to the triangle at this point, but just in terms of value in, value out, we call this fx plus h. Now, to conclude for this part of this video or tutorial on calculus, instead of utilizing this equation of delta y over delta x, which just means the change in y over change in x, which we've been describing throughout this video, well, for h, for this length here, let's utilize some coloring just for this, or perhaps some shade depending on the video or capacities. This here is x plus h minus x. That's what that is. This line here is x plus h, take away x. Say, for example, this was 10 and this was 5. Let's put these values in to make this clear. Let's say this is 5, but this instead is 11, then if you want to work out that length, you need to do 11 take away 5, and that's what it says, 11 take away 5. But of course, it's not always exact numbers to the degree that they're simple, like 11 and 5. They could be decimals and so on. So we're just going to leave it as whatever this number is, x plus h, take away x will give you the same as delta x. That will give you delta x. Now on the y-axis, you can see the same thing. If I want to find this length from here to here, which is the length of my change in y, as we've been doing so far, that length of my change in y is going to be fx plus h take away fx. Is 1.5 take away 0.5, for example. And so that would give me delta y, would be fx plus h minus fx. And we can do a little bit of stripping down. This is x, and this is also x. X take away x is 0, so there's no need to add into the equation h plus 0. So instead, I'm just going to leave it as h, leaving me with the formula that I can now use to calculate the gradients of curves, rather than just utilizing changing y divided by changing x and measuring it with a ruler or something that's, or having a scenario where the gradient isn't simple to measure because it's, for example, a straight line like y equals x, y equals 2x. We can have something as complex as a curve now, and instead utilize this equation to calculate the gradient, and that's what we'll be doing in the next section.